Hello, my name is Jorge Henrich, and I'm an undergraduate student in engineering for the Universidad Autónoma de Chihuahua. And today, with my peers Pedro César Ovalle and Daniel Alejandro Rios, we would like to talk to you about the implementation of UAVs for border surveillance and security. Nowadays, the immigration is a big problem. That is why the government of each country is starting to implement new ideas about border security and surveillance, such as the use of UAVs. This because of the facility to implement microphones and cameras on these aircrafts, and because of the wide view that they can have. Another positive point of this implementation is that these aircraft do not need a pilot. They only need maintenance occasionally. The aim of this investigation is to show the advantages of using unmanned aerial vehicles for border surveillance in Mexico, as well as defining a better use of this technology, either if it should be used in migration terms or mainly focus on crime-related issues. This study is worth because the UAVs have a lot of potential if we talk about surveillance. They are the perfect aircraft to do this kind of job because they are small in comparison to other aircrafts. Political concerns. Politics of the US-Mexico border have assumed a high profile largely because of the inflammatory rhetoric by President Trump, his proposals for a border wall. Nevertheless, in the House of Representatives, there is a political support for development of a smart wall, based on surveillance technology along the border, which is seen as being cheaper, less disruptive, and less political controversial than Trump's physical wall. Immigration status. People who are in the country without permission or illegally are called undocumented. This means they do not have permission to live in the US. They are not authorized to work and they have no access to public benefits like healthcare or a driver's license. Use of UAVs in US-Mexico border. Drones used by CBP were tracked in June 2020, traced flight paths of 7 of Predator drones. Most of the drones' flight paths were, as would be expected, close to or along the border. UAV's subsystem architecture. We consider a thick linear and hierarchical wireless sensor network, as described in the figure shown, which integrates three types of sensors: basic sensing nodes, BSNS, data relay nodes, DRNS, and data dissemination nodes, DDNS. The BSNS are elementary sensor devices forming the first layer of the architecture. They are low powered and resources and power-rich nodes used for the detection of moving objects. The alerting and the cooperative relay of messages to and from the second layer, which are the DRN nodes. UAV's electrical architecture. The electrical architecture shown in the following picture is centered around the use of well-known flight control called the KK2 board made by RC Story King. This board uses an 8-bit microcontroller operating at 20 MHz with 32 general-purpose input/output pins, I2C communication protocol, Universal Asynchronous Receiver/Transmitter UART, serial communication line, and an analog to digital conversion ADC channels. UAV's software architecture. The software design for the quadcopter is an infinite loop. The process starts with the controller input from either the user or a set of instructions set in memory. The next step is to decide the best route on how to accomplish the given input by capturing the current sensor data provided by the accelerometer, gyroscope, magnetometer, and GPS, finally returning to the loop, doing it all over again. In the Border Patrol mission, there exists a set of potential base stations and a set of determined patrol targets distributed in the border area. Considering the capacity constraints of bases and the endurance limitation of UAVs, the objective of mission planning is to locate the base stations and plan the UAV's routes to minimize the overall cost. For this, our model needs to have several assumptions. Assume that all UAVs are in the same type. The flying speed of UAVs is assumed to be constant. The UAV must depart from and return to the same base station. Each UAV can visit multiple targets, while each target can only be visited by one UAV. patrol cost for each mile is only concerned with the UAV's property. The figure presents an example of the optimization problem for the UAV base location and patrol routes. In patrol missions, a series of base stations with the corresponding equipment are essential. These stations are established inside the borderline, can be reconstructed with the existing sentry post for reducing the construction cost, or be built near the border to reduce the flight distance of UAVs. Now that we have introduced the model, we have the experimental setup, where we introduce what type of movements and operations we can do in order to optimize the flight paths. The operation of closing the base station. Two UAVs are launched for both Station A and Station B. At this time, we can try to close one of these two stations and find whether these targets can be detected by the UAVs from only one station. If so, then Station B can be closed. As we can see on the figure, where Station B has been closed and the number of UAVs has increased for Station A. The operation of up to. This relocates two targets on one flight path in a tentative solution. This operation is mainly meant to reduce the crossover routes or overlapping routes. As you can see, only the flights has been changed. The operation of exchanging targets. This neighborhood is set to swap a target with another one which locates on another path in a tentative solution. In two paths can belong to the same station or two adjacent stations. So basically, we're giving a plane more nodes and taking away the nodes from another plane. The operation of insertion. This procedure removes a target or reinserts it in another position in a tentative solution, which may change the owner base station of the target. This one basically changes the plane from their base or changes the flight paths. Basically, it's the combination of the other three operations. Now, by using an algorithm, we can determine the paths where they are only able to do the operations seen before. We are going to be comparing two algorithms, the neighborhood search, this is a popular one that joins nodes with neighboring ones, and the CW saving algorithm that focuses on the flight endurance and base locations. On table 1, after the neighborhood search algorithm, the solution is improved a lot. Some flight paths are merged and adjusted, which reduces the number of UAVs used as well as the flight distance of UAVs. For example, the routes 5 to 7 to 20 to 5 and 5 to 22 to 5 is merged into one. The one is 5 to 17 to 22 to 20 to 5, and the detecting order of target 14 and 23 is interchanged, decreasing the UAV's redundant flight. Although the number of stations has not changed, the number of drones of the UAVs has decreased after the optimization. Only 7 UAVs are used in the final solution, which is still less than the one of the initial solution, as displayed in Table 2. The overall cost has been decreased from 372,992 to 274,386, down by 26%, proving the feasibility of H1 and effectiveness of neighborhood search. On the table 2, the conclusion can be drawn that the CW saving algorithm has utilized the flight endurance as far as possible, which is obvious in the feasible solution. Compared with the cost of feasible solution in H1, H2 reduces the cost from 372,992 to 336,496. After the adjustment of the neighborhood search, the structure of the solution has changed a lot. Although the number of the UAVs has not decreased, the base station 1 is closed and replaced by other two stations, which reduce the base establishing cost. The detailed comparison is shown in Table 2. The overall cost has been reduced from 336,496 to 189,061, dropping by 44%. Therefore, H2NS seems to be more accurate than H1NS and can be solved the problem better. Now we can analyze the data from the tables before, where on the first table using the H1 algorithm, After the neighborhood search, the solution is improved a lot. Some flight paths are merged and adjusted, which reduces the number of UAVs used as well as the flight distance of UAVs. We were able to reduce the cost, and on the second table, the effects of using the CW7 algorithm as well as the combined with the neighborhood search, the H2NS, we could determine that this algorithm was the best in order to save on costs by reducing the amount of money by 44%. In conclusion, we determined an algorithm able to optimize the flight paths, aircraft numbers, base locations, and as well as the number of bases. With this, reducing the cost for the smart wall. We need to take into consideration that the best solution is the deep cooperation between air surveillance and ground sensors. So we also reviewed another measure that was the sensor network able to sense movement on the ground. If you're interested, I strongly suggest going to the following papers that we use in order to learn more about the subject. In these references, you're going to be able to see different techniques of using air surveillance and designs in order to improve border security. This is all for today, and thank you very much for your attention.